In this video, we're going to talk about the Bernoulli probability distribution, and we are interested in three specific characteristics of this distribution. We're interested in finding the mean, the variance, and the moment generating functions. So let's begin first with the probability distribution. So if I assume that random variable x follows this would be Bernoulli, so I'm going to go BR for Bernoulli with parameter P. The probability distribution, of course, is easily written. These are the possible values of random variable x. And probability of success in a Bernoulli trial is P. Probability of failure is going to be Q. Here, Q is 1 minus P. Okay, so for this one, let's begin by finding the moment generating function. That's m for the random variable x t. So the moment generating function, by definition of moment generating function, that's the expectation of e to the tx. And we can actually write this in its definitional form. The definition of expectation is e to tx times probability of x, and this is for, of course, all x, which in this case is just 0 or 1. Okay, we can go x 0 to upper limit of sigma would be 1. So for this work, we can actually now choose the value. X is 0, so it's going to be 0t times probability of failure is q, so I'm going to multiply by q plus e to 1 times t, probability of success is p. Okay, and e to 0, this expression is going to be 1 times q is q, and the next term would be e to p times e to t times p. Okay, so having that, now I can actually write q. If I think of q as 1 minus p, we can write it that way, but we can leave it like this form. But you can also have an expression entirely in terms of p. Okay, so that's the moment generating function. Now, next we want to find the mean of this distribution, which is expectation of random variable x. Again, by definition, that is sigma x px. And I'm actually going to do this two ways. I'm going to use the moment generating function in a minute, but I'm also going to the root definition of expectation. Okay, so again, just as we did earlier, I'm going to multiply 0 times probability of 0 plus 1 outcome times probability of outcome. And in this case, the answer is just going to be P. So the mean is simply P. Okay. Now I can also do this using moment generating functions. So this would be an alternative. If I look at m prime of random variable x t, the derivative of this expression, that's going to be e to t times p, right? And of course, m prime at a value as 0 will give you e to 0 times p equals p, and m prime x is indeed the definition of the mean. So m prime of x at 0 is going to be the mean, which is p. So you get the same outcome as we just did. Next, let's take a look at the variance. So how am I going to find the variance? Sigma squared of the random variable x. So the variance is now given by, we can go to the definition again. This is the definition based on sigma form, sigma x minus mu squared times px, again on all x. And so we can do it this way, or we can actually use the computational form of this, which is what I have up there is the conceptual. I'm going to call this the conceptual definition. That is the square of the deviation from the mean. That's the conceptual definition. And the other form is the mathematical expectation form, which would be expected value of x quantity squared. Okay, this would be what I call computational form of it. Now, expected value of x squared, again, that would be sigma of x squared px, right, on all x. And minus expected value of x is mu squared. Okay, and we can actually do this again. The outcome times probability of outcome, I'm doing the sigma at this point. Next one is 1 squared times probability of success minus the square of the expected value of random variable, which is mu. So that's going to just give me p minus p squared, or I can factor the p, that's p times 1 minus p, right? And because 1 minus p is q, I can write it as pq. So we have arrived at the variance of a Bernoulli random variable. The variance is going to be pq. Now we can also get this, of course, through the moment generating function again. So here's how I can do this again. The variance we just mentioned is expected value of x squared, random variable x squared, minus mu squared, right? And that's what that is. So we can actually use moment generating functions in this work. So expected value of x squared, I believe we did that up here earlier, didn't we? No, not yet. Okay, so I'm just gonna do that. I'm just gonna do second derivative, right? M double prime of x at t minus mu, which we just found was m prime of x at t, right? And of course we're going to square that, and the second derivative, right, that's m double prime evaluated at 0, of course, that's what it's going to be. So m double prime x evaluated at 0, right, minus m prime evaluated at 0 squared is going to equal 2. Now the second derivative is derivative of the first, and the first derivative, m prime x, right here, turned out to be p, but in notation, in m prime x at t is e to t p. So you're taking the second derivative of this expression actually, right, with respect to t. So the second derivative also going to be e to t times p. Let me adjust these. All of these are evaluated at t0. Okay. So m double prime x at 0, and there we go. Now I can write this e to t p evaluated at t equals 0, right? Minus the mean which we just found was p squared, right? Now e to t evaluated at 0 times p is p minus p squared. Again, you get p times 1 minus p. Again, this is using the moment generating function to find the variance, but the way I have it up here is just fine, just as good, right? For the variance is pq, and that's indeed what those turn out to be. Okay, so this, again, in this video we just showed the mean, deviation, and the moment generating function for the random variable x, where x follows a Bernoulli probability distribution.